Hello, everybody. Uh, okay, so yeah, welcome back. We are going to have another interesting session. Hope you enjoyed the last session. Like, how do you guys feel from the last session? Any comments about our sessions? Was it interesting or boring? Okay, okay then. Yeah, before going into today's session, we'll just recap whatever has happened in the last session, right? So we have seen how a star was evolving, a beautiful life cycle of a star. We saw many nebulas, molecular clouds, protostars, and how it went into a red giant or supergiant, and how it ended. It just had a supernova, and the remnant of supernova, what was it called? A black hole. So a black hole is something like a end point of life cycle of some star, right? So black holes are the absolute end, and this end itself needs another session. And that's why we are here to bring out and pull out interesting stuffs about black hole. And we'll have a beautiful journey into the mysterious and intriguing phenomena in this universe. So yeah, what do you guys think when I tell black hole? What comes to your brain? I mean, mind. When I tell black holes, singularity. Nice. Anything else? What comes to your mind when I tell black hole? Come on, guys. It's the most interesting and mysterious thing that has ever stayed in this cosmos. Okay, we have seen how a black hole is being formed, and it forms a singularity. It's a point of infinite density and infinite gravity, right? And it also forms an imaginary boundary called as event horizon, above, in which not even light could escape. That's black hole, but we can tell black hole in a simple words also, but it takes a lot of effort and involve a lot of mathematical complications to learn what is a black hole in real. So today we are not going to discuss deep into the black holes in a mathematical sense, but just to pave a way of you to understand what happens in a black hole in a mathematical way. We'll lay you a foundation for it. And let's start with asking some question. What happens near a black hole? What happens near the event horizon? Do the laws of physics even, exist inside a black hole? What's there inside a black hole actually? And I hope this session would be very interesting than the previous one. And let's start the journey. So yeah, so even we are learners and we tend to make mistakes. And even if you have any doubts, you can put it up in the chat, and we are here to clarify it. So yeah, we are not going to deal with calculus or differential equations or probability or whatsoever physics topics or mathematical concepts. We'll lay you a foundation. Okay, it's like you don't need to worry anything about whether you need any prerequisites of mathematical foundation. We are here to teach you from the scratch. But I wish you all have a pen and paper with you so that it's very easy to understand whatever we are teaching. So to give a brief idea about what this session would be, we'll introduce to you what's a black hole, and we'll give you a historical content of it, and we'll tell you why is general relativity important to learn about black holes, and some mathematical foundation so that you'll be able to understand the metrics in general relativity and how are these metrics gave us a good coordinate systems, and how are these systems transformed, and how are they extended, and what is the real graph or something that we see today, and look into some advanced black hole solution. I mean, we are not going to derive any solutions over here. We're just going to put forward the ideas and what made them give such kind of solution and beautiful equations, right? So we are here just to put forward the solutions. Okay, so and then we'll look into what's a Penrose diagram. That's the maximum extended diagram one could ever have, and look into what's an ergosphere, what's a Penrose process, and at last we cannot leave our Stephen Hawking. He gave the beautiful phenomena of Hawking radiation, and at last we'll end with few paradoxes which exist in black hole physics. So let's start. So when I tell you black hole, I think these are the images which comes to your mind, isn't it? Right? How many of you have thought this? Can you give any thumbs up? A black hole would be really like this. Come on, guys. Haven't you thought the black hole would be really like this? Cool, cool. So actually, when the first image was taken, that's not what it was. It was actually a blurry, a donut-shaped image. And this is the reality. You may expect something more colorful or something, but the real image of a black hole was this one. It was actually taken on April 10, 2019. I mean, not taken, it was released on April 10, 2019, which was captured by Event Horizon Telescope. Can any one of you tell what's the galaxy in which this black hole belongs to? Wow, M87. Nice, nice. Yes, it's M87. So this black hole belongs to M87 galaxy. It's in the center of its galaxy. And can any one of you tell what's there in our center of Milky Way galaxy? I mean, there is a answer already. Yeah, it's Sagittarius A. Yeah, yeah, cool. It's Sagittarius A, which is there present in our center of our galaxy. And yeah, here black hole things we cannot take picture of it, but yeah, we are an intelligent ape who would do that. Okay, next we are going just to brief how was the image taken and what do we gain from that. So Event Horizon Telescope, it's not a single telescope, but it's actually a global network of radio observations. These observations were present in a lot of places like Hawaii, Arizona, Spain, Mexico, Chile, and Antarctica. So these were the places where telescopes and observation centers were placed, and the informations were collected in petabytes, which involved millimeter wavelengths. Can you guess why this millimeter wavelengths? Actually, if it is millimeter wavelength, it could penetrate to thick clouds of gas so that we can capture the image of black hole like quite precisely, right? So that's why they used millimeter wavelength and collected all the data in petabytes, and then they gathered in a place and used complex algorithms and produced this image. And it actually started in 2017 and it went till 2019. So why was this image so much celebrated? It actually confirmed the black hole existence. During those times, people were thinking black hole is just a hypothetical solution from Einstein's general relativity. But this image actually confirmed the black hole even do exist. And they were able to study more precisely about size and shape of the event horizon. Even they were able to learn what an assertion does and its dynamics. So next to go into it, let's see some historical moments. How did black hole even come? Who named it and whatever? Let's see, in 1915, Einstein was the first one who released his general relativity. He told, see everybody, gravity is no more something a weird force. It's actually a curvature of space-time. In 1915, he released his field equations, a set of 10 equations. And in 1916, there was a guy called Schwarzschild, and he solved his equation and he told, hey, look, I'm getting a very weird object. I assumed it to be spherical. a normal object which is not rotating with uncharged, and he found quite a beautiful solution for Einstein's equation. And then in 1960, John Wheeler was the first one who termed it to be black hole. Until then, it was some object which is, having a mysterious physical phenomena. And 1960, John Wheeler was the first one who popularized this term black hole. And in 1963, Roy Kerr, he told, see, we also have black holes which are rotating. So he found solution for rotating black holes. And in 1965, Penrose came and he told singularities are inevitable one in the black holes. And after that, there were many milestones in human history, like Stephen Hawking came, we took the first image of black hole, and there was so much of progress in black holes, discovery. But these are the quite few things which we are going to discuss in today's session. So how they were able to come up with these solutions, and a lot of interesting stuff we are going to discuss. So let's see. So to start with the anatomy of a black hole, so I'm going to point out the parts of a black hole. So I want you to guess what's it's called. So the center of the black hole, what is it called? The arrow which is pointing, what is that place called? Singularity, right? Yes, it's singularity. So what's a singularity? As I have told earlier, it's a point of infinite density and infinite gravity, right? So once a star goes to supernova stage, it just ends and core collapses into a single point. That's called singularity. And next I'm pointing towards, actually it's a circle. It's a boundary, imaginary boundary. Can any one of you guess what's the name of this imaginary boundary over here? Like after which there's no light. Event horizon, yes, it's event horizon. So what does it do? It's actually a boundary which let nothing, not even light, can escape from it. So what's our next eye-catchy thing over here? It's this disk. What's this disk called? Assertion disk, right? It's assertion disk. So what does an assertion disk do? Well, if a black hole starts pulling things into it, it obviously have some matter which is spiraling around it, isn't it? And this matter heats up and it emits some radiations. And this is called assertion disk. And also to add up, there will be some, you know, lensing effect, which is like caused due to stars or galaxy behind it, due to the large gravitational force. It caused some lensing effect. It might not be seen in this image, but generally this it happens in a black hole. Okay, so let's go through some of the important results of relativity. I wanted to put this slide because just to give you a rough idea, and we are not going to deal with the mathematics, not much of mathematics, but we'll see what are the important results which came up from the relativity concept. First thing, time is no more a constant, uh, field or something. It's a dimension. It's a fourth dimension. Einstein added time as the fourth dimension, adding to the 3D space which we live in. And the second thing he told was, see, light has a constant speed. No matter how fast you go, relative to you or whatever, the light speed remains constant. Right? This was the important result of relativity. Okay. And faster you move through space, slower you move through time. This result we will be proving in this session, so no worries, we'll talk about this later. And gravity is a curvature of space-time. This was one of the biggest imagination which Einstein would do. Yeah, so because gravity once was thought as a force that is like acting vast distance between two celestial objects, but Einstein told, see, I have a simple idea. It's a fabric of space-time. And gravity is simply the curvature of space-time, isn't it? So next is time slows down around heavy object, and even this result we'll be discussing in today's session. And next is gravity travels in the form of waves. So this is also one of the important results of relativity. So we have seen results of general relativity. But to look, why is general relativity even important to understand black hole? We can tell it's a mass, I mean, an object of infinite mass, and why can't we use the same Newtonian physics which we have already learned about? Well, if you see, let's assume there's two mass m1 and m2 which are under rest. Then this formula works well and fine. It's like working perfect. But let's assume two objects start to move. This actually starts to move either away from each other or towards each other. It doesn't matter, but actually it starts to move. Then what happens with this formula work? Well, one would take the instantaneous distance between these two objects when they are moving and then calculate it with using this formula and find an instantaneous force at that particular time, isn't it? So what happens is that when you consider that distance, I mean the distance at that instant, the force seems to change immediately, meaning the information is transferred at infinite speed. But wait, this is not consistent with special relativity. Einstein already told the fastest speed if anything would achieve is the speed of light, that's c. And now how is the information transferred at infinite speed, isn't it? So that was a problem which is caused in not only in gravitation, we also have that problem in electromagnetism. So in case of electric force, Maxwell was like a great physicist. He told, well, only if you consider it as a force it's a problem, then I'm going to consider electric field theory. And this was quite successful before Einstein even, popularized relativity. We all learned about Maxwell's electric field equations. But when Einstein was thinking, okay, if electric field theory exists, why can't a gravitational field theory? So Einstein came up with gravitational field theory, but it was more complicated. Why was it more complicated? Well, uh, if there is acceleration should be different for different particles. Suppose let's take there is an electric field and electric field E and it's having a mass m1 m2 m3, then the acceleration for m1 m2 m3 would be different because the acceleration is given by q e by m. But here in case of gravitational field it has the same acceleration. If you put m1 m2 m3, it just falls, it falls or it just rotates according to the velocity which we are pushing them, right? But eventually, all the particles in some small region of gravitational field have the same acceleration. This is something very weird. So Einstein told, so let me assume a fabric of space-time that is like something like this. And if I drop a mass, it bends. And this is gravity. So he told, so this assumption will make my equations very simpler. So now gravity is no longer a force, it's a curvature of space-time, right? So now how is it related to black hole? Well, if you see the sun bends this fabric of space-time a bit, and white dwarf is heavier than sun, so it bends a little more than that. And neutron star is more denser, so it distorts space-time a lot. And black hole is something like it creates an infinitely deep funnel or a well, and at the infinite distance there presents a singularity. It seems like a funnel, right? You see, it's a funnel, and event horizon, it's an imaginary boundary which is present over here, right? And this is how light behaves when a black hole is present, and this is why we see lensing effect and all those stuffs. Okay, now I would like to call Ayman to continue this presentation and give you a fundamentals of mathematics which is needed to understand black holes.
Is my screen visible?
Yes.
Okay, so now thank you, Mridula, for that introduction into the ever fascinating world of black holes. We are now going to get started a little bit into the mathematics behind what goes on in a black hole. Okay, so now we're going to start from something which all of us have been familiar since our school days, which is the Pythagoras theorem. So what does the Pythagoras theorem say? It relates the length of the sides A, B and the hypotenuse, which is the longest side C of a right angle triangle, and gives us an important relation which we will be using later on. So this relation is that the sum of the squares of the sides of the right angle triangle is equal to the square of the longest side of the right angle triangle. In other words, it's nothing but a square plus b square is equal to c square. Now a little bit more in depth into the Pythagoras theorem. Now we are going to see about the Pythagoras theorem in 3 dimensions. In 3 dimensions. Supposing we want to find the distance from the bottommost left corner to the topmost right corner of this cuboid. And we have the length of the cuboid as x, the breadth as y, and the height as z. So the first step that we're going to see is to calculate this distance between the bottom 2 corners of this cuboid. And according to Pythagoras theorem, which we had learned earlier, this distance is equal to under root of length square plus breadth square. In other words, it's square root of x square plus y square. Now we our ultimate goal in this was to calculate this distance between the bottommost left corner and the topmost right corner. So now we consider this right angle triangle. We take this right angle triangle into our consideration. And the two sides of this right angle triangle is square root of x square plus y square as we had calculated earlier, and the height of the cuboid, which is z. Now again we employ the Pythagoras theorem, and we do square root of under root of x square plus y square the whole square plus z square, which gives us the final result as square root of x square plus y square plus z square as the distance between the bottommost left corner of the cuboid and the topmost right corner of this cuboid. Moving on, now we're going to learn about something known as the Minkowski spacetime. So up until now, we have come across formulas for only 2 dimensions and 3 dimensions. So Minkowski spacetime is something that involves 4 dimensions. In this setting, the 3 ordinary dimensions of space are combined with a single dimension of time to form a 4-dimensional manifold for representing a spacetime. So Minkowski spacetime is the main mathematical description in the absence of gravitation. It combines the inertial space and time manifolds into a 4-dimensional model. Minkowski spacetime is a 4-dimensional coordinate system in which the axes are given by x, y, z, and c, t. I'll explain later on why the speed of light is multiplied with time. The formula for the Minkowski spacetime is f square is equal to minus c square t square plus x square plus y square plus z square. Now, some of you might be wondering why we have an iota, the complex number I over here. In Minkowski spacetime, we are dealing with a 4-dimensional manifold where the time component has a different sign convention as compared to the spatial dimensions. Sign convention is also something which will be explained shortly. The iota here is not directly used, but just to indicate the difference in relationship between the space and time dimensions. Now we come to a more graphical explanation of the Minkowski diagram. So what you're seeing here is something known as a space-time diagram. So what is a space-time diagram? A space-time diagram shows the position of objects as time passes. Space-time diagrams are important to visualize some useful ideas in special relativity. These diagrams in particular are known as Minkowski diagrams, where it's only CT versus one dimension of space, and it's a special class of space-time diagrams. One of the reasons why we use CT here is because the units of both the axes will then remain same, and it will be meters in this case. Now, supposing we have a ball which is placed 3 meters away from the origin between these two axes. And assuming the ball is at rest, and now we want to plot a graph between CT and X for this ball. Time can never remain constant. So as we plot the graph, for the position of the ball, we get a straight line parallel to the CT axis, and this line is known as the world line. Whenever a line is plotted on the space-time diagram, it is called a world line. In special relativity, an event is something described by t, x, y, z, but here we are using only two dimensions, t and x. In the theory of relativity, the fastest that an object can move is the speed of light. Now, supposing we have a photon which moves with the speed of light instead of a ball, then the world line is 45 degrees inclined to both the axes. That's why we plot CT on this axis so that the fastest objects in the world can be visualized easily. As I had explained earlier, for a photon, the world line is 45 degrees inclined to both the CT and X axis. Now, supposing we have an event A which has already occurred, and now we have another event C which has occurred. Two events are said to be causally connected if the occurrence of one event sends some sort of signal to the other event before it starts and causes it to start. An event C is said to lie above the 45-degree line of the photon, and an event C lies above the 45-degree line of the photon if A and C are causally connected, which means that the occurrence of A has sent some sort of signal to C. And this signal travels with a speed less than the speed of light. Now, supposing we have another event D which has occurred after the occurrence of A, then a signal would be sent from A to D in a speed that's faster than the speed of light. So we know that nothing can travel faster than the speed of light. So the events A and D are not causally connected, and therefore they are known as independent events. Now, in coming to the event B, which has occurred after the occurrence of event A, then that means that a signal has been sent from A to B with the speed of light, and this is the limit. This is the limit of causally connected events. So the maximum speed in which a signal can travel from A to B is the speed of light. Now, supposing we have an event that's plotted on the space-time diagram and we draw two lines of 45 degrees from it. This leads to the formation of something known as a light cone. We'll be coming to what is time-like, light-like, and space-like sometime later. But for now, light cone. What is a light cone? A light cone is a path that a flash of light emanating from a single event, localized to a single point in space and a single moment in time and traveling in all directions, would take through space-time. Because signals and other causal influences cannot travel faster than light, the light cone plays an essential role in defining the concept of causality. In a flat spacetime, as the one that we are seeing here, the future light cone of an event is the boundary of its causal future, and the past light cone is the boundary of its causal past. For an event E, the set of events that lie on or inside the past light cone, or V, would also be the set of all events that could send a signal that would have time to reach E and influence it in some way. Likewise, the set of events that lie on or inside the future light cone of V would also be the set of events that could receive a signal out from the position of V. And what would happen if any event lies on either the left side or the right side? Then those events are not causally connected to the event E, and those events are known as independent events. That's about light cone. Now we're coming into a term here which means metric. So what is a metric? Metrics define the distance between 2 points in space-time interval. The two metrics that I'm going to be discussing about today is the Minkowski metric and the Schwarzschild metric. So, and the difference between the two is the Minkowski metric corresponds to a flat spacetime. As you can see, spacetime is represented as a flat fabric, while the Schwarzschild metric corresponds to a curved spacetime. So any mass is kept upon the space-time fabric, it curves, and for that we have something known as the Schwarzschild metric. Now coming into one of the important fundamentals of general relativity, it's the Einstein's field equations. As you can see here, I have mentioned it in plural, even though we have just one equation. Actually, this is a set of 10 equations, as Mridula had mentioned. Yeah. So Einstein's field equation relates the geometry of the spacetime to the distribution of matter in it. Coming to the terms, this capital G here is known as the Einstein tensor. I'll shortly be explaining what is a tensor. Lambda here is the cosmological constant. Small g is the metric tensor. K is the K. This K is actually the Greek letter kappa. So kappa is the Einstein's gravitational constant. Capital T is the stress energy tensor. When capital T is 0, this field equation represents an empty space, which is vacuum. This kappa here, the constant value is 8 pi capital G divided by C to the power 4. Now, what is a tensor? In mathematics, a tensor is an algebraic object that describes a multilinear relationship between a set of objects related to vector space. It can be thought of as a multidimensional array. It's also something invariant under the change of coordinates. So now, as you can see here, we have a subscript of mu and nu for all the tensors that are mentioned here. So the values of these mu and nu can range from 0 to 3. So these tensors can be visualized as something similar to a 4 cross 4 matrix. I'll be showing you a few tensors later. So as I said, the range of mu and nu is 0 to 3. So if we say capital G 0, 0, then that means it's the first element of the tensor. And capital G 3, 3 would be the last element of the tensor. And as we vary these values of mu and nu, the value of the tensor would also change. So the first term, capital G, is known as the Einstein tensor, and it represents the curvature of space. The second is the cosmological constant, an amount of energy, positive or negative, that's inherent to the fabric of space itself. The third term, small g, is known as the metric tensor, which mathematically encodes the property of every point within spacetime. The fourth term, kappa, is just a product of constants, and it's known as Einstein's gravitational constant. It's the counterpart of Newton's gravitational constant, capital G, that most of us are more familiar with. The fifth term, T, is known as the stress energy tensor, and it describes the local energy in the vicinity, momentum, and stress within that spacetime. So as I said, this is actually a set of 10 different equations because, like I said, these tensors can be visualized as something similar to a 4 cross 4 matrix, and they are symmetric tensors. So therefore, instead of 16 equations, we are getting only 10 different equations from this Einstein's field equation. Now, more about the Minkowski metric. So the Minkowski metric equation in its differential form is the spacetime, the ds square here is the spacetime interval squared is equal to dx square plus dy square plus dz square minus c square dt square. And when this Minkowski metric is manifested in the form of the metric tensor, we get this thing here. And now we notice that the time has a negative sign, which is something very unusual. Let's see why it happens. The Minkowski spacetime, the appearance of the negative sign in the metric signature, is a fundamental aspect that distinguishes it from the normal Euclidean space of XYZ or spacetimes with other signatures. The metric of the Minkowski spacetime has a specific signature conventionally denoted as negative, positive, 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 or it can also be positive, negative, negative, negative. This signature refers to the sign of the components of the metric tensor in the coordinates of t, x, y, and z. This negative sign indicates that the time component of the metric contributes negatively to the overall spacetime interval. In contrast, the spatial components are positive, and this reflects the fact that time behaves differently from space in the context of relativity, where two intervals can be negative for events that occur at different times, while spatial intervals are positive. The negative sign in the Minkowski metric is crucial for preserving the causal structure of spacetime. It ensures that the space-time interval is invariant under Lorentz transformations, which are the transformations that leave the speed of light invariant. This invariance is a cornerstone of special relativity. Thus, the Minkowski metric tensor corresponds to a different geometry than what is used in classical mechanics and normal Euclidean geometry. Now, this tabular column represents the classifications of the space-time interval, where the quantity ds square represents the squared spacetime interval between two events. The sign of ds square determines the nature of the interval. The first one here is a time-like interval. If ds square is less than 0, then the interval is time-like, meaning the events can be causally connected and could potentially influence one another. This tabular column is in direct connection to another slide which I had shown earlier. Yes, this. So if ds square is less than 0, then the interval is time-like and it could lie here. And if ds square is greater than 0, then the interval is space-like. And if ds square is equal to 0, then the interval is light-like. When ds square is equal to 0, the interval is known as light-like or a null interval, indicating that the events are connected by a ray of light, and it's the limit of connection of two events. So two events are causally connected. The maximum speed in which a signal could travel from one event to another is by the speed of light. The third one is when ds square is greater than 0. This is known as a space-like interval. The interval is space-like, meaning the events are separated by distance in space and cannot influence each other causally, and they are known as independent events. Now, we now are progressing from the Minkowski metric, and we have now come to something known as the Schwarzschild metric. In Einstein's theory of general relativity, the Schwarzschild metric is an exact solution to Einstein's field equation that describes the gravitational field outside a spherical mass, on the assumption that the electric charge of mass, angular momentum of the mass, and the universal cosmological constant are all zero. This solution is a useful approximation for describing slowly rotating astronomical bodies, such as many stars and planets, including the Earth and the Sun. This metric was given by Carl Schwarzschild in the year 1916, as Mridula had mentioned earlier. Now, coming to the terms here, this 2gm by c square is actually something known as the Schwarzschild radius, which we'll be deriving later. T is the time coordinate as measured by a clock located infinitely far from the massive body and stationary with respect to it for r greater than rs. R is for r greater than rs, the radial coordinate measured as the circumference divided by 2 pi of a sphere centered around the massive body. This term here, the d theta square plus sine square theta d phi square, can also be written as d capital omega square depending on the source that you use, where omega is a point on the sphere. Theta is known as the polar angle and it's the colatitude of omega, angle formed from the north in radians defined after arbitrarily choosing a z-axis. Phi is the azimuthal angle and is the longitude of omega also in radians around the chosen z-axis. And this formula is applicable for spherically symmetric bodies. Now, once we combine the terms, we get three components here. The first one, the temporal or the time component, reflects the gravitational time dilation near a massive object, It shows that clocks farther from the mass tick faster compared to clocks closer to the mass. The next one is the radial component. It determines the behavior of radial distances in the curved spacetime around the mass. It describes how radial distances are stretched or contracted compared to Euclidean space. The third one is the angular component. The angular component indicates how spatial distance in the angular directions theta and phi are affected by the curvature of spacetime. So when we calculate this space-time interval here, basically we are finding the trajectory of matter near the black hole. And what are the different sign conventions that could be used? So the first one that could be used is positive, negative, negative, and negative for time and the other coordinates. This would lead to the ds square being mostly negative. And we know that when ds square is less than 0, it's a time-like interval, as I had mentioned earlier and shown in the graph before that. The other sign convention which could be used is negative, positive, positive, and positive, where negative is for time and these three is for the other three coordinates. This would, when we use this sign convention, then the ds square would mostly turn out to be positive, which indicates that it's a space-like interval. And when we use this sign convention, the formula has to be slightly modified in order to get this. And these are the only two sign conventions that we can use, nothing else. We are free to use either one of this, but should be consistent with it. Now, when we represent the Schwarzschild metric in the form of the metric tensor, this is what we are going to obtain. And something which I had not mentioned earlier is that the Schwarzschild metric is for a mass that's spherically symmetric, non-rotating, and uncharged. And this something known as the Schwarzschild radius is 2gm divided by c square. Now, what is singularity? Singularity in mathematics is when a function is not defined. For example, if we take the function 1 by x, then it has a singularity at x is equal to 0. Schwarzschild solution has singularities at r is equal to 0 and r is equal to rs. Since the Schwarzschild metric is expected to be valid only for those radii larger than the radius r of the gravitating body, there is no problem as long as r is greater than rs. This is mostly the case for ordinary planets and stars. For example, the radius of the Sun is approximately 700,000 kilometers, while its Schwarzschild radius is only 3 kilometers. Therefore, the singularity at r is equal to rs is an illusion which can be removed by choosing a different frame. This is the main reason why we again need a new coordinate transformation into Eddington-Finkelstein coordinates or Kruskal coordinates, so which Mridula will be discussing later, so that the metric becomes regular at r is equal to rs, and we can remove the confusion here. However, at r is equal to 0, it has a gravitational singularity, and the metric cannot be extended in a smooth manner. But at r is equal to rs, we get something known as the event horizon. So can anyone tell me what is the event horizon? What are your thoughts on it? All right, so in astrophysics, an event horizon is the boundary beyond which events cannot affect an observer. It's often described as the boundary within which the black hole's escape velocity is greater than the speed of light. Once a particle is inside the horizon, moving into the hole is inevitable. According to gravitational collapse models, which we had studied in the earlier session, an event horizon forms before the singularity of a black hole. As some of you might know, matter can never be seen falling into a black hole. While approaching the hole, the object will seem to move ever more slowly, while any light it emits will be further and further redshifted. One would need to know the entire history of the universe and all the way into the infinite future to determine the presence of an event horizon, which is not possible for observers. Therefore, no experiment can be performed within a finite-sized region of space-time and finite time interval that answers the question of whether or not an event horizon exists. Because of the purely theoretical nature of the event horizon, the traveling object does not necessarily experience strange effects and does, in fact, pass through the calculated boundary in a finite amount of its spacetime. Now, another question for you. Does the Schwarzschild metric, is it only applicable to black holes or can it be applicable to other bodies of similar features also? Okay, so the answer is yes, it can be applicable to other bodies which are spherically symmetric, non-rotating and uncharged massive objects also. So the surface at the Schwarzschild radius acts as an event horizon in a non-rotating body that fits inside the radius. The Schwarzschild radius of an object is proportional to its mass. Theoretically, any amount of matter will become a black hole if it's compressed into a space that fits within its corresponding Schwarzschild radius. For the mass of the Sun, this radius is approximately 3 kilometers, and for Earth, it's small as 9 millimeters. But the Sun and Earth do not have the necessary mass to overcome the electron and neutron degeneracy pressure, which Shruti had discussed in the previous session. The minimal mass required for a star to collapse beyond these pressures is the Tolman-Oppenheimer-Volkoff limit, which was also discussed in the previous session, which is approximately 3 solar masses. Here we find an interesting coincidence of the Schwarzschild radius with Newton's gravitational constant. First, let us calculate what is the escape velocity. The escape velocity is referred to as VES, V with a subscript of Vs here. Now we use the principles of conservation of energy. Kinetic energy is half mv square, and taking the datum as the event horizon, below the datum we take the sign convention as negative, and we get the potential energy as minus gmn by r, which is equated to 0 as the total energy. And equating both sides, we get the escape velocity VES as square root of 2 gm by r. Now, as I had said earlier, in the event horizon, the boundary which the black hole's escape velocity is greater than the speed of light. So escape velocity is said to be greater than the speed of light, and substituting the value of escape velocity here, we get the value of what is known as the Schwarzschild radius. Now, how do we convert from Schwarzschild radius to Schwarzschild metric to Minkowski metric? As we know, as I had mentioned, Schwarzschild metric is corresponding to a curved spacetime, and Minkowski metric corresponds to a flat spacetime. We need to go from Schwarzschild metric to Minkowski metric, which is curved to flat. So mass curves this spacetime fabric, as I had shown earlier, at infinite distance from a mass which is very far from the mass outside the gravitational influence. In regions far from the massive object for larger r, the term 2gm by c square r becomes negligible. Therefore, the Schwarzschild metric approaches the Minkowski metric in spherical polar coordinates. The other way in which we can go from Schwarzschild to Minkowski is when there is no mass. When mass is equal to 0, again the space-time would be flat. So what I'm telling here is, yes. So we see this term here. So either we can put mass is equal to 0 or r is equal to infinity here, and this term would vanish. Then the Schwarzschild metric would look similar to the Minkowski metric, depending on which change we do. So either one of those changes, either one of these could be done in order to convert Schwarzschild metric to Minkowski metric. And now over to Mridula to continue more about more coordinates related to these metrics.
Okay, thank you, Ayman, for explaining deep into the mathematical foundation we needed to understand black holes. And there is a confusion why we are selecting this kind of coordinate system and what's the difference between coordinate and a metric. We'll soon, learn what's the difference and why are we learning new coordinate system. So basically, you can imagine it like choosing polar coordinates between polar coordinates and Cartesian coordinates to calculate the area of a circle. Like suppose you wanted to calculate the area of a circle, which coordinate system will you choose? Like we'll obviously go for polar, right? It's very easy. But the absolute answer for calculating area of a circle, it's pi r square, no matter what Cartesian system you take, or no whatever coordinate system you take, the answer to the question, that is the what is the area of the circle, remains the same. Metric is something which describes the geometry, like whether the light rays move straight or will it turn towards turn 45 degrees or something like that. To describe the light rays, we tell it metric, and we learn more deep into that. So till now the end of you guys, and we learn more about it. So fine. So why do we need new coordinates? So I want you to revise what's the problem with Schwarzschild. What are the two radius? That is, what are the two R values which we felt difficulty with? Can any one of you put tell me in the chat box? What are the two R values which we are having difficulty with? Come on, guys, just to revise whatever you have learned till now. Okay, basically, yes, R equal to 0 is one of the point. What's the other point? Yes, R equal to 0 and R equal to RS. Nice. So you are remembering stuff. So let's again look into this equation. We keep showing this equation so that you will, understand and you will picturize this equation. So this is Schwarzschild equation. So when you put R equal to 0, the metric blows up, and R equal to RS, again it blows up, right? So that's why we need a new coordinate system. Basically, at R equal to RS, it's not a true singularity. It's something of a coordinate singularity, which it shouldn't happen. But according to, due to poor choice of coordinate system, we are having this kind of problem. So let's quickly say what would Schwarzschild geometry would look like, and we no longer call this geometry, and we called it as geodesic. What's a geodesic? Basically, the path that objects flow when they are moving under the influence of gravity. So suppose you're having a black hole, as I was shown in the earlier, like in the first part, the intro part of the session, I have shown you that the light rays bend near black holes, and this bending of paths is called geodesics. And assuming a particle just flows into or goes into a black hole, how does that even affect the path? That's called geodesics, right? So now look carefully into this picture. So this is the graph you see. One coordinate is Schwarzschild time coordinates, and then here is the R part. And throughout this session, we will assume the angular part of the Schwarzschild metric is 0, and we are going to travel radially. I mean, we are not going to, swirl up like this and go. We are just going to straight go into black hole in order to make our equations and mathematical stuffs more simpler. Right. So let's see. See the light cones here. At a far distance, they are at 45 degrees. I mean, the light cones are bending towards 45 degrees, and it's, there is no bending. And as you go nearer and nearer the event horizon, it seems to bend and get narrower, right? Why do they even get narrower? So any guesses? Why are they getting narrower? Okay, basically, why they are getting narrow is because look into this, you know, equation carefully. You are going to reduce R value, and you are going to, increase the M value. So eventually, it leads this time term to decrease a lot. And this, decrease in time coordinate and increase in the radial part, which eventually lead to this narrowing. Okay. And we have seen near a heavy object, the light rays bends. And this is why it causes this light cones to bend and get narrower and narrower. At event horizon, it points straight up. And if you see inside black hole, that's after below event horizon, the light cones are tilted towards the left side. And it's like nothing. Your future would be the singularity. This diagram just tells you the future is singularity. And okay, now this diagram is more of a complicated thing. Let me show you a simple picture. So now you see this image, forget the rest of the image, and you see this image carefully. So as you go nearer and nearer, your light cone seems to get narrower and narrower and narrower, and it seems to go till infinite. Right? It goes till infinite time, and it seems like as if you're not going inside even horizon. You're not possible. You're not even allowed to go inside even horizon. But the ingoing light beams of singularity appears as if the object is coming from infinite time and falls into singularity. Why this is even happening? Like if nothing could cross this sort of boundary over here, then how are even black holes formed? And how does it even suck objects inside? So this is like complicated, right? So this is the problem which Schwarzschild coordinate system was facing. So you see here, so how do we draw this diagram? Suppose I gave you like x is equal to y plus c. So what kind of geometry would you do? It's a straight line, right? You draw some straight lines over this graph, right? And now the equations are ct is equal to minus r minus 2gm by c square ln mod of c square r minus 2gm plus some constant. This is the geodesic equation. This is the equation which describes ingoing light beams. This is to describe outgoing light beams. So what is an ingoing? This light beam you see here, right? This is ingoing light beams. And this light beams which are pointing away from event horizon, it's outgoing light beams. Okay, so this is, just look into this equations carefully. This are geodesic equation. And we are not going to look into how these equations are derived because it's more of a complicated mathematics stuff. So we're just putting forward the equation, the geodesic equation of Schwarzschild metric. So basically this happens due to poor choice of coordinate system. So let's see what, let's have some simple example why this is happening. So let's take a Earth, like a Earth is a 3D globe, right? So when people are trying to put it into a 2D map, there is a lot of distortion, right? Why do we need a 2D map? Just for a simplification, just for a easy convenience purpose, right? So we take a Earth and project it into a 2D map, and there are a lot of distortions, isn't it? So you have a Mercator projection where the angle and the shape are remaining the same. You see, Africa is still Africa. It's so beautiful. Like there is no distortion in its shape or something, and the angle between two places are still same. But one thing to be noted is Greenland and Africa are of the same size. This is not something that should happen, right? Africa in reality, it's 14 times larger than Greenland. Basically, the area got distorted. So people came up, okay, area got distorted. So Gal Peters map was something that would describe the area very well. But you see, the shape of Africa is being distorted very to a large extent. You see, everything is elongated, right? So similarly, all the maps over here has their own purpose. Their own purpose to, like, suppose you need to travel a long distance. Even Google Maps use Mercator map, and suppose you need to calculate the area of countries and continents, you use Gal-Peters map. Similarly, you can assume Schwarzschild metric is something, its geometry is something that is unable to describe one of the things which we wanted, and it distorts event horizon and singularity to a large extent. So this is why we are facing difficulties. You see, projecting simple 3D Earth into 2D map has a lot of distortions. Like it has complications like preserving one feature and leaving the other to get distorted. Similarly, we are projecting a 4-dimensional time and radial system. So this is more complicated, isn't it? So people are trying to come up with new coordinate systems so that we remove a few distortions, right? So let's see what people did to solve this thing. So till now we have seen what Schwarzschild metric was and how was it geodesics and what its problem is. So now let's see who came up with a new solution or new coordinate system and how was it transformed. So to look at again, we have seen this equation 3-4 times in this session. So we'll again look back this, but just look into this equation. This is Schwarzschild equation. And next what happens is that we are going to give you the geodesics of Schwarzschild equation. So, and two things I wanted you to remember. When a coordinate system is described, uh, two most important things you should remember is one is the line element or the interval between two events, that is ds square element, and the second thing is the geodesics, like what we have described here, to put it onto a map, a 2D map. So these are the two things which are important in a coordinate system. And this geodesics should have a time-like coordinate and a space-like, that is r coordinate, right? So now let's see. So Eddington was one of the person who came up with this transformation, and he was like, see, there's a constant over here. And let me start with this constant and no more complication. I'm going to assume it to be u. And this constant is going to be a null coordinate. A null coordinate is something like a light-like coordinate. You have seen time-like, light-like, space-like, right? So similarly, this constant u is going to be a null coordinate. So now he took this constant as u, and he, sent this part left side, and he got u is equal to ct plus r plus 2gm by c square, ln mod of c square r minus 2gm. And he started his calculation with this ingoing light beams. But why did he leave the outgoing? Let's discuss this later. So, but initially he just started with the ingoing light beams, thinking he could solve the problem. So he started his work and he told use a null coordinate, and he got a beautiful line element for u and r with u and r. But the problem is u is still a null coordinate. We need a time-like coordinate, isn't it? He got, I mean, this is the line element of Eddington-Finkelstein coordinate with consisting of u as null coordinate and r as space-like coordinate. But what is the problem? We need time-like coordinate, isn't it? We need one time-like coordinate and one space-like coordinate to represent it, in a graph. So Eddington was, he wanted a time-like coordinate. So we are going to make a time-like coordinate. And he assumes CT dash, that's our new time-like coordinate, as u minus r. That's so simple, isn't it? You see what's u minus r? It's ct plus 2gm by c square ln mod of c square r minus 2gm. So the same thing he got. And one more thing, guys, I wish you had a paper and pen so that you can note it down these things. So it's very easy to understand, right? So let's come back. So Ct dash is equal to u minus r. So this is something that you could tell. So Ct is equal to Ct dash minus 2gm by c square ln c square r minus 2gm. And now what he does was substituting in the equation 1 and 2. What is equation 1 and 2? It's the line element equation. And the second one, what's the second one which is important to describe a coordinate system? Like one is the line element, and what's the other that describes a coordinate system? Line element, and what's the other equation? Okay, this time I'll tell you it's geodesic equation. But remember two things that is very important to describe a coordinate system. One is the line element and the other is the geodesic equation. So we have got a beautiful equation for Eddington. He was very satisfied. See, he got geodesic equation, he got a line element with time-like coordinate and space-like coordinate. So he was happy with this. And very important thing that you should notice, now you substitute r equal to rs. I want everybody to substitute r equal to rs and tell me what is going to happen. What would happen if you substitute r equal to rs? Just a try, guys. Would it blow up or it wouldn't? Just tell me, would it blow up or it wouldn't? S for blowing up and no for not blowing up. Come on, just put something. Substitute R equal to RS, and okay, what is RS? It is 2gm by c square. That's RS. So when you substitute R equal to RS, okay, it would blow. Okay, think properly and think properly. So you substitute R equal to RS in this equation, and you are going to substitute R equal to RS, and this term vanishes. Let's assume this term is vanishing, and this term stays like that, and no problem in this. R equal to RS, no problem in this term, and this term is also fine. So the line element is not going to blow up. It's not going to become infinite, right? It's some finite value. So one problem which we had earlier is now solved, right? The coordinate singularity is removed, isn't it, guys? The coordinate singularity is now removed, and the interval is well defined in the region 0 to r less than infinite, right? So I hope I'm clear with this. So if you have any doubts, you can ask me till this point. Let me just revise. We had a Schwarzschild coordinate, right? We had a Schwarzschild coordinate metric like this, and we had two geodesic equation, like this is for ingoing and this is for outgoing, and we took only one ingoing, just ingoing equation, and we solved to get, we transformed to get another beautiful line element and geodesic equation. So this is a new ingoing geodesic equation, and this is a new line element. And we solved one of the problem, that is the coordinate singularity, that is being removed now. So I hope I'm clear till now. Any doubts? Fine. I hope there's no doubt and it's clear till this point. So let's see, and let's try to plot it in the graph. Well, beautiful. The ingoing geodesics are continuous and it's looking very awesome. Yes, the problem is solved now. And let's try to plot the outgoing geodesics, that the lines which are coming out of singularity, right? Well, this doesn't seem to solve, isn't it? The outgoing light beams are still discontinuous. Why are they happening like that? So one thing is that when Eddington was trying to solve Schwarzschild problem, he started to solve only the ingoing light beams, isn't it? He solved the ingoing geodesic equation, and he didn't go for outgoing, right? So that's why the outgoing light beams are still discontinuous and the ingoing are continuous. So let's have a simple look of what is happening. Let's take a waterfall, like some waterfall that is called black hole. Let's assume that waterfall to be a black hole, and the water is flowing downstream. Okay, the water is flowing down the stream, and let's assume a leaf, some leaf, as a particle or as a ingoing light beam. Okay, and this leaf, yeah, it seems to come down very smoothly with no any objections, right? It came down very smooth. And now let's take a fish. Okay, a fish is trying to go upstream. Okay, a fish is trying to go upstream. Obviously, what happens? The fish would not be able to go up, isn't it? Because the water is flowing downstream, and our perception is that it always flows downwards. Right. So here also our perception will be we are trying to solve ingoing light beams, and we are not, you know, looking into the outgoing light beams. This actually depicts well the physical scenario, that is anything that will cross event horizon but eventually will not come back of event horizon. This is a well depicted physical scenario, but then Einstein was like, okay, maybe I should solve outgoing light beams, and he tried solving with this equation. And then what happened was that ingoing light beams became discontinuous. What happened here? The outgoing was fixed. It was very good. It's a straight line and it's continuous, but the ingoing light beams become discontinuous. So, well, okay, you told me that Eddington finger-sync coordinate depicted a physical scenario, and here it's like graphically we are seeming like everything is pushed out of event horizon and nothing will enter an event horizon. What do you think this is? Everything is being pushed out of event horizon and nothing is entering. Nothing would be able to enter the event horizon. What is this actually? White hole, right? It's a white hole. So basically, this is the first time mathematically white hole was like found, but people didn't recognize it as a white hole because already Eddington is having a problem with his coordinate system. So he thought it's something like, okay, there's a problem with mathematical problems, so this is not the right way. So to revise, this is the two geodesic equation of Eddington, or the equations. And now Kruskal was there. He was like, Eddington, see, look, you're having quite a simple problem. It's a small problem. So Kruskal was like, okay, let me solve it. So Kruskal came. He told, see, first look into your geodesic equation. It seems to be very similar. So he thought, let him do differential equation. And he found, so just look into this differential equation. What's the difference between these two equations? Can any of you tell? What's the difference? Just look into this equation and this equation. It's a plus and minus sign change, isn't it? It's just a difference of a plus and minus sign. So Kruskal was like, man, this is very simple. So let me first try to solve your geodesic equation into a simple form, and then let me transform it into my way, and then let me bring a time like and space like coordinate, right? So what he did, he multiplied du and dv. He multiplied du and dv, and he got something like this. When he took out this factor out common, he got 1 minus of 1 minus 2gm by c square by r c square dt square plus 1 minus 2gm by c square r whole inverse dr square. What is this, guys? What is this bracketed term? Like, can any of you tell? It's like, we have seen this 3-4 times in this session, like more than 3-4 times. It's a term very often we have seen in this session. Or let me give you an hint. It's some interval. Okay, basically it's the interval term in the Schwarzschild coordinate system which we have seen. See, look, it's the ds square term. So Kruskal was very happy because he simplified this interval or the line element term into very, very simple, right? It's very simple, isn't it? It's having just du into dv term. And now what he was thinking is, and one more thing to notice that, as I have told earlier, we are neglecting the angular part and we are assuming that we traveled radially. Okay. And now Kruskal was thinking, maybe if I try to make the equation into an exponential form, it might, you know, uh, stretch and compactify the spacetime. So he had u dash as e to the power c square u by 4gm and v dash as minus e to the power minus e square v by 4gm. And one more thing is, what Kruskal is actually doing is, like, Kruskal coordinate system is similar to Mercator system, which we have already looked at. See, Mercator, what is Mercator? Basically, Mercator tries to focus on same angles and same shape, isn't it? That's what Mercator 2D projection would do. And Eddington was similar to Calpidus, right? He was not caring about angles and shape. He just was like, I'm going to solve this problem, and he was trying to do something else. So Kruskal was trying to simplify all the issues which are caused in this coordinate system, and he came up with u dash and v dash. And what's our next step? What's our next step, guys? What's the thing present in ds square? It's du and dv, right? We need to find du dash and dv dash and substitute instead of du and dv, right? So we are going to find du and dv in terms of du dash and dv dash, and the only term which creates a problem is this u minus v. So u minus v is also substituted, and Now, one thing I want you to note is u minus v term has only r. That is the radial term or the space-like term. So here comes the hint for the next step, which we are going to discuss. But before that, how does the line element would change? The line element would change something like this when you substitute this one here. Okay, it would become minus 32 by r into gm by c square whole cube into e power minus c square r by 2 gm into du dash into dv dash. So now what's the next step? We have to find some time-like and space-like transformations. So already I have given you a hint. This u minus v term is completely space-like. So this is what even Kruskal was thinking. Kruskal thought, wow, u minus v is completely space-like. Then what would u plus v be? Wait, what would u plus v be? Come on, guys. What would that u plus v term look like? So here is u and v. So what would u plus v look like? It's a very simple term, and I want any one of you to put the answer forward here. What would u plus v be? Any guesses? Would it be time like or space like, or what is the u plus v term? Yes, it's 2CT, right? Okay, nice. So people are concentrating, and yes, we are about to end, guys. I mean, we are about to get to a fully nice coordinate system. So yeah, so u plus v would be time-like coordinate system, and this is what even Kruskal was thinking. So he came up with v as a new time-like coordinate and u as a space-like coordinate, capital V and capital U. Okay, and this now what's the next step? What is the two important things that we should find to completely have a nice coordinate system? What's the two things? Okay, I'll give you a hint. One is the line element, that's the ds square, and what's the other? What's the other equation which we should have to describe a complete coordinate system? Or only with that we yes, geodesic equation, right? It's the geodesic equation. So first we'll be finding line element equation, and the second which we'll be finding the geodesic equation. Very beautiful, right? So we got du dash and dv dash as something like this when we do differential, and we substituted that in this line element equation. And when we solve this equation, you will get u square minus v square is equal to square r by minus 1 into e power c square r by 2gm. Nice. So this is the final changes we are going to do to the coordinate systems, and Crystal was the last guy who finished the complete coordinate system. Okay, but we need to plot the graph, and now we are going to plot the graph with Crystal, like how Crystal was doing. So first what he did was, see r equal to r is something beautiful happens. So substitute r equal to r is, what would this equation become? Like any one of you put it in the chat. What would happen if you substitute r equal to rs? U square minus v square is equal to what? Just give me the value or some equation. Yes, 0, right? U square minus v square would become 0. And u square minus v square 0, in a sense, what would happen? It's nothing but v is equal to plus minus u. And when you try to plot it in this graph, you'll get two straight lines, isn't it? It's very beautiful, right? So now event horizon is very simply be able to represent in two straight lines. And this two straight lines, doesn't this seems familiar, guys? Like something like a cone. And what cone is this? So this cone is the same which we have seen in the Minkowski diagram. Like this is the light cone, right? Like, but not the light cone, it has the event horizon. But just to be consistent with the diagrams or the geodesics, and we are still consistent with Minkowski and Schwarzschild and whoever we have come to, right? So now we are done with r equal to rs, and what's the next point? R equal to rs is done. So we are going to now look into r equal to 0. So okay, let's substitute r equal to 0. R equal to 0. What type of equation would that be? Like, would it be the same straight line or parabola or hyperbola or a circle? What type of equation would that be? Like when I substitute r equal to 0. Or let me show you the equation once again. See, this is the equation and just substitute r equal to 0 here. What would happen to this equation? Like u square minus v square would be something, right? What is that? Some constant only, guys. Like it's not a very big uh, exponential. Well, you are going to substitute r equal to 0 here also. So look at this and just tell me what u square minus v square would become. Minus 1, right? So u square minus v square would become minus 1. And what is that equation? It's an hyperbolic equation. So let's see. It's an hyperbolic equation, and how a hyperbola represented? It's actually having y-axis as its main axis, and hyperbola is like this, right? So we have got a beautiful hyperbola for singularity, and this hyperbola represents singularity. And now what's this region is the remaining one, which we all know this is our universe. So we are going to substitute as r greater than rs. So when we substitute r greater than rs, we still get hyperbolas, but with its axis as the u-axis. So we get a set of hyperbolas representing the outer space, right? So I hope I'm clear with the Kruskal's, geodesics. Right. So you may think like what happens if R is less than RS? Like we'll discover it in a quite time, like in 2 or 3 slides, we'll discuss about it. Before that, I wanted to show you graphically like how things would change. And yeah, no more like complicated maths here on. Just we are going to see graphical images and graphical transformations. To just summarize, we were in Schwarzschild and we went to Edmington, and he had a problem of he solved actually one of the rays but couldn't solve the other. So Kruskal came and he was like, see, now all the angles are now at the now the angles are at 45 degrees. The light cones or at the lights are at 45 degrees, and the angles never change as you go even into the black hole. The 90-degree you can see right here is not going to change, right? This is the major thing which Kruskal's coordinate is, benefitable, or you can assume something like that. And we have seen hyperbolas for singularities and straight lines for event horizon, and the rest of the set of hyperbolas for rest of the universe or space. So just to show you how are they transformed, here's a simple video for it. So you see how the Schwarzschild is being transformed into a Eddington. It's just a map is being compressed, or changing the lines. Right. So next we'll see how Eddington from this graph and how it went to Kruskal in a visual way. You see it's being pulled and stretched and compactified. And this is how Kruskal was very interesting in his coordinate system. See, you see, this is the singularity, right? And future always point towards up. It's always upwards, right? So further modifying the coordinate system, what people did was uh, we have to, contract the entire space, the entire universe into a simple diagram. Then we would do something like this. This is r equal to infinite, and this is at infinite distance, okay? And this is our infinite past, and this is our infinite future. And suppose you are somebody here at the center, and your light cones would be like this, right? It would be pointing towards up into the infinite future, and your past would be something in the infinite past, right? And this is the event horizon. And why are we simplifying the singularity into a straight line? Just to represent it, guys, just to make it simpler. Okay, so next, now we are going to see what's going to happen inside. Well, it's a kind of mystery and it's more complicated than we think. But one thing that we were able to find mathematically is the time and space coordinates are going to interchange their roles. What do I mean? Does it seem very bizarre or something? Well, to understand it mathematically, first we'll understand mathematically, and then we'll see what was it implications of it interchanging its role. So first, let's take the mostly positive system. That's the Schwarzschild metric that we have seen so many times in this session. This is the metric, okay? And let's revise what's time like, light like, and space like. If it's less than 0, that's because the time coordinate here is negative. So if it's less than 0, it's time like, and the rest of the radial part or the angular part is positive due to, I mean, the r square term. So the ds square is greater than 0 for space like terms, right? And if it's light like, it's the interval is going to be the 0. Okay, so since we are inside black hole, just substitute r is less than rs. Okay, and due to angular, I mean symmetric part, spherical symmetric part, we are going to neglect this angular part. Okay, so first what we are going to do, neglect this angular part and substitute r is less than rs. What do you get, everybody? What happens is that 1 minus rs by r would become negative. Right, this term you see, if r is less than rs, this 1 minus rs by r would become negative. You see, this is like greater than, I mean, less than rs. So it's less than this rs by r is greater than 1, and thus 1 minus something which is greater than 1 would be negative, right? So dt square, now it would become positive and dr square would become negative. So what does that even mean? The time coordinate is becoming positive and it's going to act space like, because the ds square is greater than 0, right? So it's going to act space like, and the radial component over here is going to act time like, because it has a negative over as its coefficient, right? So it's going to act its time like. What does that even mean physically? So actually what happens is that the singularity, as we have seen in the Kruskal diagram, let me show you. So you see the singularity over here is no longer a space, right? It's not a place in the space, right? It's going to be a moment in time. Like you cannot avoid singularity once you are into event horizon, right? So you know that time flows unidirectionally. It's like always towards the future. Now what happens is that space is going to act time like, and this makes space go in one direction. Like once you enter event horizon, you want to travel in one direction, and that is absolutely into the singularity. And time coordinate, I mean the time component is going to act space like it's no longer time is only the future. Like it's possible to travel past or even future, whatever, wherever you want to go, you're free to travel. So this interchange of its role makes more complex system inside the event horizon or inside the black hole. So let's see something. This is how the light cones would be like when you try to go into the event horizon or into the black hole. You see the light cones are like, you see here your future of the light cone is entirely inside black hole, right? It's like if you are inside, if you are in the event horizon, your entire future is inside black hole. You cannot escape it, isn't it? So this is why you obviously fall into the black hole and not even light could get away from event horizon. So this is something which everybody should like got to know now. So now let's see. So when you are like here, okay, and we have a black hole over your future, like you are at the point here, and it's the event horizon. You are at the event horizon, and your entire future would be black hole. But what would the past be? It, can anyone answer what would come here? This is our entire universe, and this is our black hole. And what would the past of this rocket lying over here, which has the entire future to be black hole? White hole, right? So, okay, there's a question. What did you mean traveling? Okay, basically, it's not traveling to the past. The time coordinates become space-like. It's like, I mean, it is uh, possible to travel in any direction. It's no more unidirectional, right? That's what I mean. Like the time is going to become space, and space in space you can travel in any direction. You can go forward, you can go backward, you can go sideways. So similarly, light inside a black hole will act space-like. It can travel in any direction, and that's why it's more complicated inside a black hole. And we are not having, I mean, not much idea of what's happening inside. So I just wanted to put some idea, or I mean something about what's happening inside. So I just gave you this part. Right. So okay, coming back. This is black hole and this is white hole, right? White hole basically comes from the mathematical solution of Kruskal also. Like when Kruskal was trying to, solve the equations, he had his exponential term, right? When he solved the exponential term, he got plus and minus sign, and he got a beautiful symmetric, image like this. This part was plus plus, and this was plus minus, and so on. We had. So this part belongs to white hole, something like this. And due to the symmetry, we also have another part lying over here. What would that be then? Like this is the universe, okay, well defined. Black hole, okay, it's like we have taken the first image and it gives us the confirmation. And white holes, okay, a mathematical solution, hypothetical solution, but still not verified. But what is this unknown thing? Parallel universe, right? Exactly, parallel universe. So parallel universe is something like it's entirely same as whatever the composition our universe has. It may be like there might be another you who is lying, I mean, who is like listening to the session in the parallel universe. But yeah, and then there were physics who was crazy. Like they were like, okay, it's okay, there's a knot over here, isn't it? There's a lot. And physics are very craziest people. They were like, okay, and what happens when I try to cross this knot? And it's very easy, right? I'll be able to travel from our universe to the parallel universe. Would that even be possible? No. So okay, no, it's hypothetically, okay, let's take an hypothetical situation. Would that be possible? Okay, still no. Okay, fine. Yes, we will not be able to pass through this, but this kind of node is like having a wormhole over there. What happens is that, see, like you are suppose here and your light cone is always pointed towards upwards, it's not going to turn like left or right. So if you wish to travel through this node, you should be traveling at the speed of light, which is like impossible. Like even if you're lying over here, your future light cone would be this way, isn't it? So it's like impossible to travel through this node. That's one possible solution. And in case you're going through this node, okay, and we have a wormhole over here, and that wormhole would be something like this. Even that wormhole is, it would first be short and then elongate, and then again short and then become elongate, and then it has a discontinuous here. It's like if you enter a wormhole, first it would be a shorter distance to see the next universe, the parallel universe. But as you keep going, you keep going for the infinite time, and you never reach the next universe or the parallel universe. Right. And one more thing about this diagram is that black hole white hole composition like this, like the diagram which we are seeing here, should, like, this kind of black hole should be existing from the time of our earlier universe. They should not be formed from stellar collapse. If it's from a stellar collapse, it's very evident. It's like a star which collapsed, and it's like it's belonged to a universe, and it doesn't have a white hole and all. So this is one point which should be cleared. And yeah, this is the perfect diagram or the complete extended trapezium Penrose diagram. And like, what's a Penrose diagram? It will be discussed further. And this is the complete diagram. This is our universe. This is black hole. This is white hole. This is parallel universe. And this is the way which we are going to travel. This is wormholes, and they are even mathematically not possible. Right. And these two universes, I mean, this universe and white hole is hypothetical situation and still not yet confirmed. Right. So next I would hand over the presentation to Shruti, because like you see, the black holes not just be stationary, and it's what shall assume the black holes to be spherically non-rotating, non-charged, objects in space, but there are black holes which are rotating, because you see, even sun, this simple mass object, is rotating. So why not black holes? So I would like to call Shruti to continue this session.
Invisible.
Yes.
Thank you, Ayman, and giving me the very
Voice
beautiful
is little uh, breaking, Shruti.
speaking.
Not breaking, light. I mean, if you increase
Feeble.
your speaker. Yeah.
Volume. Okay, okay. Now is it audible?
Yeah, better.
Uh, uh, I'll continue. Guys, let's now talk about the types of black holes. We have already seen that Schwarzschild black holes that have
Shruti,
more
voice
mass.
is still low.
Oh,
Uh, Still the voice is low.
wait a minute. Wait.
Shruti, your mic is off if you're trying to speak anything.
Now is it audible? Or is it still low?
Yeah, you are audible.
Hello?
Yes.
Now is it audible,
Yes.
Mridula? Better?
Better, I guess. You can continue.
Uh, I don't know what. Okay. Guys, I also have to inform you all. We might be going like a bit extra time. Yeah, definitely. Like, yeah, we all are enthusiastic in telling about stuff, and I hope You guys will be okay with taking a little bit of extra time. Is my screen visible now?
Yes.
Yes.
Okay. Okay, guys. So yeah, we have seen about short-shelled black holes, and we know that they are black holes that have no charge and they basically don't rotate. And now let's dive right back into black holes that rotate, the Kerr black holes. Uh, Rotating black holes are more complex than our beloved sweet short-shelled black holes. The metric that describes this is this one that you're all seeing in the screen right now. So yeah, let's try going from Kerr metric to Schwarzschild metric. Like first, we'll see what the metric is. Ts square. I mean, it's a very complicated looking equation, and we have these small variables, not variables, substitutions. A is, sigma and delta. So basically, what is introduced new here is A, and this A is there in sigma as well as delta, and others are all just r and theta. So A is j by mc, where j stands for the angular momentum of the black hole. So yeah, this A is that entity that makes, I mean, describes the rotation of the black hole. So if we are going from Kerr to Schwarzschild, can anyone guess how to get from here to Schwarzschild? Like guess, because Schwarzschild metric is like Schwarzschild black holes are stationary and uncharged, and Kerr black holes are rotating and uncharged. So can anyone guess what we should do to this metric? A equal to 0, yes, but yeah, make J equal to 0. That's the thing. We have to make the angular momentum as 0, which means the black hole is not rotating, so it's stationary. So A will become 0. Then sigma, I mean, yeah, let's go to the next slide. Yes. So J equal to 0, we get A equal to 0. Then sigma will become R square and delta will become R square minus RS into R. And RS is the Schwarzschild radius. So substituting these values into the curve metric, we will get this, where instead of sigma I've put r square here, instead of delta r square minus rs, and yeah, everything here. Since a is 0, it goes off, this goes off, and this goes off, and r into sine square theta d phi sine square theta d phi square will remain here. And then for doing further algebra, we'll get this equation, which is the Schwarzschild metric. This is how we go from Kerr to Schwarzschild. Uh, Schwarzschild black hole, like Mridula was telling about the anatomy of a black hole at the very beginning, that has event horizon and singularity only, right? Hmm. Kerr, just because it rotates, has several parts to it. It first has an axis of rotation because obviously it rotates. And now the event horizon is not just one layer but two layers, an inner and an outer event horizon. Buckle up, guys, but we can see only the outer event horizon. Yeah, we can see only that because it is the surface of no return. So how did we even know, uh, when we cannot even how did we even know the existence of inner horizon when we cannot see beyond the outer event horizon? Uh, that's because, remember in the last session I was talking about some non-vacuum Schwarzschild metric during TOV equations derivation. I mean, I didn't derive. I was just telling that we have to derive it from the non-vacuum form of Schwarzschild metric. Yes. To recap, non-vacuum form basically tells us about how the black hole is inside. I mean, inside. Uh, so the vacuum form is the metric that describes outside the black hole. So non-vacuum form is inside. So physicists came up with the non-vacuum form of Kerr metric as well, and it had suggested that there can be an inner horizon. Yes, can be. We do not know for sure if it exists because obviously nobody has been through it. Yeah, since nobody has gone through it yet, we do not know for sure that an inner horizon exists. Of course, except Cooper, who Morse coded quantum data onto the watch that he gave to Merv. Sorry, guys. So far, so good. But the most interesting part is this region between the outer horizon and the static limit. I'll tell about static limit in a while. So first, I'll explain ergosphere and then I'll go to this outer stationary limit surface. So, ergosphere is the shaded region where the objects in that region will move only in the same direction as the rotation of the black hole. It cannot move in the opposite direction or remain stationary with respect to an observer outside the black hole. So now coming to that blue line that's called the outer stationary limit surface. Why is it called that way? Because beyond that surface, an object cannot be stationary with respect to an observer outside of the black hole. At the stationary limit surface, an object can remain stationary if and only if the object is moving at the speed of light. I want to talk more about this stationary limit surface, but I don't think this time, so I'm moving on. So Schwarzschild now looks easy, right? All these complexities occur only because the black hole is rotating. And this is not just it. There are two other complex solutions for which we will be discussing uh, uh, shortly, but we won't be going into the depth of the math behind it because it's beyond the scope of this session. Now, wait, outer horizon is only the point of no return. So, even if we are in the ergosphere, we can get out of the stationary limit surface, right? Yes, and a particle coming out of the ergosphere actually slows down the rotation of a black hole. Oh, so the black hole loses energy when an object from the ergosphere escapes. So, wait, can we actually extract energy from the black holes? Yes. And this is the fancy name. It's called the Penrose process. The process of extracting energy from a black hole. Sounds cool, right? But unfortunately, if any black hole lies in our vicinity, so that we can even try extracting energy, then we would already be spaghettified. Just kidding. Anyways, Penrose has pointed out that we can extract energy from a black hole hypothetically. So we can make a particle go beyond the stationary limit surface of a black hole and get into the ergosphere, then get out of that and actually make the black hole slow down a bit. So, since black holes lose energy, that energy is transferred to the particle that comes out of the ergosphere because, yeah, obviously, outer event horizon is the point of no return, not the stationary limit surface. So the math behind Penrose process is also way beyond the scope of our session. So we decided to make it a bit more theoretical and attached to it the anatomy of the Kerr black hole. That is the ergosphere speciality. In a further session, maybe we'll try doing more about the Penrose process and the other stuff which we told beyond the scope of our session today. So yeah, moving on. So remember the field equation that we have shown way before? That uh wait, let me show you that. Uh yes, this one. Yeah, this one. This is the Einstein's field equation, right? So um coming back, is it not going? So basically what we are going to do more is that there are more solutions to that equation, not only Schwarzschild and Minkowski and Kerr. So there are other two that we are going to discuss today, the Reisner-Nordstrom equation and the Kerr-Newman black hole. Yes, these two. So Reisner-Nordstrom basically is a stationary and a charged black hole, and Kerr-Newman is basically a rotating and also a charged black hole. Let's see what a Reisner-Nordstrom black hole is. This is the metric of that. And as we see these two, I mean, this term of the whole metric is only the extra stuff from the Schwarzschild metric. Remember, Schwarzschild metric was only till here. So yeah, this is, Reisner-Nordstrom uh, describes a stationary, that is non-rotating, but charged black hole. Before going, we'll try again. We'll try going from Reisner-Nordstrom to Schwarzschild. So can anyone guess how to go from Reisner-Nordstrom to Schwarzschild? And I and yeah, Reisner-Nordstrom is just has charge and Schwarzschild doesn't. Body. Okay, since we have a time constraint, I'm moving on. We just yes, I mean not RQ. Yes, yes, but what is, I mean, RQ is zero, but how? Yeah, charge is zero. Yes. We basically make charge as zero over here. So first let's see what RQ is. RQ, as I've written here, is this formula, and this has that Q that actually gives the black hole a charge. So if Q is zero, then RQ term vanishes. So this term will go to zero here, and we'll get back our beloved Schwarzschild metric. Fine, right? I know it's a lot to take in, so let's quickly recap. It's always good to have a zoomed out picture of what we are trying to learn. So we started with black holes, like a very brief description of what they are, their history, and then we dived into Pythagoras theorem, which indulges with the shortest distance between 2 points, and then we went to 3D, then to 4D, Minkowski, then that describes the flat space time, by the way. And from there we went on to the math a little bit, the metrics, metric tensor. Ayman would have guided you well through it. Metric tensor, space like and time like separation, interval rather than distance. Then we went to Schwarzschild metric and in Schwarzschild coordinates. Then we faced an issue. We encountered a false singularity at r equal to rs, which is just a flaw of Schwarzschild coordinate. And we knew from the Riemann curvature tensor that we have only one true singularity at r equal to 0. So then Eddington and Finkelstein decided to fix that false singularity at r equal to rs, and they made one of their constants in the geodesic equations as their coordinate. Then it solved the problem of having continuity at r equal to rs. So there's only one singularity, but still that continuity was only for ingoing light rays for a black hole. Then Kruskal was like, why not try making the outward going light rays too as continuity? And also he solved it up and then made the light cones, and now the light cones are at about like 45 degrees. So then from Kruskal we modified even more, and then we arrived at that trapezium, and then from that trapezium we arrived at white holes, and then the parallel universe and the whole Penrose diagram. And from Penrose diagram we came to the other solutions of the field equation, the Reisner-Nordstrom, and sorry, first we started with Kerr, then we went on with the ergosphere and the Penrose process, then we jumped to Reisner, Nordstrom, and Kerr-Newman, but we didn't go into the math of Reisner, Nordstrom. We just saw how we can go from Reisner, Nordstrom to Schwarzschild, and we didn't even show the metric, Kerr-Newman metric yet. So that's, I mean, anyone wants to see it. It's complex. It's very complex, the metric, the Kerr-Newman metric. You know what? It's okay. I'm going to show you all. I'm excited. So yeah, this is that Kerr-Newman metric, and yeah, this looks complicated, right? To be honest, even I have no idea how this works. It's beyond our level. We are just second years, and this is like graduate level physics. So yeah, I think that's enough. Going back. So the four types of black holes that we saw today are the Schwarzschild, which is a stationary and uncharged black hole, the Kerr black hole, which is a rotating black hole but is uncharged. This rotation alone makes it complex enough to deal with. Then we went to Reisner Nordstrom, which is a stationary black hole but has charge, and it's not as complex as Kerr though. Kerr Newman is both charged and rotating, and it's the most complex of all. These complexity variation is present only in theory and is the good way to learn till Kerr Newman. But all black holes have mass, charge, and angular momentum. These three entities are like unique for each black hole, pretty much like the quantum numbers that we studied in structure of atom in 11th. So sadly, all of them are best explained by the most complex Kerr-Newman metric. So yeah, I'd like to call upon Kishle to take over the session for an interesting characteristics of black holes.
Uh, is it
You're
visible?
muted. Yes, yes.
Yes.
Okay. Thank you, Ayman, Shruti, and Mridula for the amazing presentation. Now I'm going to ask you a question first. You have learned about the whole thing, how black holes theoretically get introduced in physics, and after the prediction from field equations, Schwarzschild metric, and whatever we have learned till now. We get the first picture in 2019. So, but there is always a question: is this black hole going to be eternal in this universe forever, or is there any end of black hole too? Can you put in the chat who thinks that black hole is going to be eternal? Yes, no, whatever. If it ends, how it will end? Okay, black hole evaporation, nice. But I would like to say that it is a kind of eternal, not totally eternal. It is a kind of eternal. Okay, we'll see how this works. So, for things, see, y- so to understand how black hole will evaporate, or so we have to understand that what is going to emit. matlab how we have to understand some basic. We have to go to the start of the class 11th that we learned is thermodynamics. So can anybody state the second law of thermodynamics? We will understand from the very basic. Now there is no maths. So we can put it in math way, but I like the theoretical way much. Okay, it will be end by emitting generation ice. Can anybody put the second law of thermodynamics in the chat? Entropy increases, nice. Okay. So basically, one of the basic idea of the second law of thermodynamics was that if you have an isolated system, you can't decrease its entropy anyway. Isolated system I'm talking about. In this case, our universe is going to be an isolated system. So basically, you can't decrease its entropy. By any process, it doesn't matter on the process. It will always increase or remains constant. So, but there is a problem with a black hole if you go from this way. So when if you have black hole nearby you, then you take some thing and just throw it in the black hole. you can tell that from the observer that you know that you throw something that it is going to be constant. But in our universe, just exclude a black hole. In our universe, there is nothing. matlab, our entropy has been decreased. We have to increase that. But we don't know what's inside the black hole. Is it going to increase its entropy or not? So there is a much way easier way to know that if we know that how we calculate the entropy of black hole. So I think you get the idea what I'm trying to say. To repeat that, I want to tell that you have a block, say it a ball. You just throw it into the black hole. What happens? The overall entropy of from our universe. I'm treating black hole as a separate system. Has been decreased, but you don't know how the entropy gets changed within the black hole with that ball. So you can't tell that overall entropy is going to increase or decrease. To understand this, we have to know how to calculate the entropy of black holes. Can anybody tell that how we calculate the black holes entropy? And this was a nightmare of many scientists for many years. How we can calculate the entropy of a black hole? Okay, nice, nice. So basically, Benkestein was the first who proposed that by knowing the area of event horizon, we can tell that whether its entropy increase or not. So the surface area of event horizon is going to be the entropy factors, but that is going to measure of the entropy of a black hole. So basically that's the idea. If you have a ball or system, you just throw it inside the black hole, then its area of the event horizon is going to increase. And from the outside observer, we can tell that, yeah, something increased in that black hole, and overall the second law of thermodynamics doesn't violate from our perspective. So this is the whole idea. But this was the idea, but there is a problem with this idea. Entropy and temperature are not two different things. Whenever you have to talk about entropy, then you always have to think about temperature. The temperature is the intrinsic value of entropy. Because we are talking about event horizons area now. There is nothing. The event horizon is there is a question at what does it depend only on area, not volume. So for that, that was only a proposal from Bekenstein. Basically, event horizon is not something that have volume. It is just a surface from where your gravitational collapse is going to too much that light can't escape. So its surface area will make more sense than volume. It is infinitely thin, thin, thin. That's why area. So basically, question was that how the entropy without temperatures doesn't make any sense. It means that black holes have their own temperature. So just think about it. What it means that black holes have their own temperature, but how is it even possible? Because I know many of us know that black body radiation theory. So from the black body radiation theory, anybody that have radiation temperature, it have to emit some radiation. So how a black hole that's that's basic property is to sucking everything. How it can emit anything. So basically, when close your eyes and just think about black holes. What comes in your mind? Just tell me. A black round sphere that is sucking everything. But how it can emit anything? Just think about this. This was the problem, the very big problem in the physics society, physics community till Hawking get the answer. Right. Okay, nice. Okay, I will come with that. So basically, to understand this problem, we have to understand few to understand this problem's solution. We have to understand something that is stuff of quantum theory. The quantum theory here comes to the answer this question. This is how Hawking thinks. So basically, first thing is false vacuum. So basically, anybody can tell that what is false vacuum. I know some of you have known that thing. So basically, I have time constant. I have to just finish it fast. So basically, they in quantum field theory, there is a field theory that tell that whatever present in this universe, a particle, call it a particle. It comes from excitation of the fields. Just take example like you have seen an electron. So electron is nothing but just excitation and de-excitation of the electron field. So when you excite the electron field, then electron pops out, appears in the real world. So this is a quantum field. This is one of the result of quantum field theory. It looks like very theoretical, but everything has their mathematical proof. I don't want to get into that because it will be very, very, very vast and out of our scope. So basically, this was our field theory. And second thing is Heisenberg uncertainty principle. I know many of you knows the Heisenberg uncertainty principle in your high school. You have learnt about that. So basically, Heisenberg uncertainty principle states that you can't measure position and the momentum with 100% accuracy. If you find position 100%, then there will be infinite or some deviation in momentum stuff. So basically, now let's break the momentum part. Momentum part is nothing but m into v. That is velocity. So basically, you can't measure position and velocity at the same time for a particle. So can anybody tell what is velocity? Tell me what is velocity. Can't we say that change in position, rate of change in position is the velocity? So basically, here position and change in position is going to be Heisenberg uncertainty principles constant. So in similar ways, when you say there is a vacuum, so vacuum means nothing. No particles is there in that region. That is the vacuum region. So basically, when you state that it is vacuum, then you are telling that it the field, the excitation or the excitation in the field is going to be zero, and its rate of change of with respect to time is going to be zero. So basically, it violates Heisenberg uncertainty principle in the same way. So because you can't say there is something called true vacuum. So to nature doesn't violate. We know that Heisenberg uncertainty principle is very basic, fundamental in nature. So it doesn't break in that way. So uh, to save the Heisenberg uncertainty principle, so virtual particles pops up and pops down in the vacuum. It's appear on its own and it disappears on its own. Annihilate, you can say that in sense. But doesn't it make any paradox kind of thing? If something it is you have nothing and you're creating something from nothing. How is it even possible? So first thing that can come in mind is we have nothing at all at the first, and some particles with some energy comes. How is it possible? Doesn't it violate the conservation of energy, which is much, much, much more fundamental in physics? So basically, it doesn't violate in some way. So call it a virtual particles appears. So it will have one pairs call it particles and another pairs call it antiparticle. So it particle have some positive energy and what antiparticle have some negative energy. So basically, overall energy of that system is going to be zero. So we are not violating any kind of energy conservation laws. So basically, this is what we from the very start we know all this thing. But what master stroke from Hawking that he tells that during near the event horizon we have that whole thing with a vacuum. So virtual particles pops in pops out. That's fine. So the thing is that gravitational energy is there one virtual particles tell that it appears. So it will have one pair. One is going to be a particle and another is going to be antiparticle. So particle have positive energy and negative and what antiparticle have negative energy. So basically both of these things have some kind of energy. So black hole what will try to suck them both. So basically it will try to suck them both, but there is some probability that the particle with positive energy can escape. It have some positive energy, and gravitation energy is going to be negative. So basically, if overall energy is going to be positive, so there is a possibility that particle with the positive energy can escape. So this happens, and the particle with negative energy, it is destined to go in a black hole. Or there is one more case that both go is in. We are not considering that case. So basically, one part is particle is going to uh, is escaping from the black hole. So for the we will observe that oh wait, what I am saying, black hole is emitting something. How is this even possible? So this was the one of the result of Hawking's theory of radiation. Hawking radiation. You tell that. So this is how black holes can emit anything. But in the context of black holes, what black holes we see is that he gets some negative energy, and from the E equals to mc square, the Einstein thing, the black hole will lose some mass because it gets some negative energy. So negative energy is equivalent to negative mass here. So it will lose some energy, and it will shrunk a little bit. So I would like to after the whole analysis and doing mathematical, this Stephen Hawking comes to this thing, this formula, the most famous Hawking equation. Here you can here you can see that temperature is basically inversely proportional to mass of black hole. So if mass is very going to be very low, then temperature will be very high. And the larger the mass of the black hole, its temperature is going to be less. So I know today we are going a little bit more mathematical, but physics is all about mathematics. So we have to also know this fact that physics is not going to be always like you knowing facts, fun facts, or whatever cool facts. Deep behind that, there is a very long research thing. There is a very deep and hard work of research that you will have to understand. So basically, here, so basically, it black hole gets shrunk a little bit once it captured that what antiparticle or non negative energy thing. So when it gets shrunk, so little by little by little, one day will come when the black hole will completely vanish, and that is called evaporation of the black hole. It will evaporate, and no one knows how it is going to be happen. So basically, there is a one also cool fact here. So a black hole with the mass of the sun would take up completely 10 to the power 67. Just think about this. In just I want to compare these things. Our universe has only 13.6 into 10 to the power 9 years old. The Big Bang was only 13.6 into 10 to the power minus 9. Why? 10 to the power 9 years old. So basically, you can tell that black hole is eternal in some case. But some case in this way. So basically, there is something else that this theory get confused with. It is that once black hole get evaporate completely, what will happen with that information that it contains earlier? What it sucks out it during its whole lifetime? It has it has sucked the planets. So what happens with that information? It is destroyed. So to understand this, can anybody tell that what is information in your sense? Can anybody understand what is information actually? I know I today I'm going a little bit fast, but there's something called time constant here. Can you tell me what is information for you? Oh, okay. So basically, information is a he was that allied cosmic is almost right. Information is basically arrangement of something, certain kind of arrangement. We all are made up of electron, protons, and neutrons. But what makes us different from the chair that you are sitting on? We all are made up of same thing. The thing here different is the information, the arrangement that is in his atom and in mine atom. This is the major difference. So there is a theory in quantum mechanics that information can never be destroyed, no matters what you press. It can just change the shape. And if you just uh, again read the whole situation, then you will get the information back. So no matter what process you did in whatever, even if you just burn the paper, its information is never going to destroyed. You can retrieve, but we don't have that much of technology till now. So basically, but in the case of black hole, it is not in this way. It just evaporated on its own. We even don't know how it's evaporated. So what happens to that information that it sucks during his whole lifetime? There are several theories upon this, and one of the theory was that this information helps us to make a new universe. So this is how everything is going to be connected. This is one of the theories, and there is theory that it got lost. We even don't know where it got lost. But these are all theories. We have to go get in the mathematics of this, because ultimately mathematics is the language of universe. So basically, with this, I will conclude. There is a lot of paradoxes that I want to share with you, just like firewall paradox. There are a lot of paradoxes, but with the time constraint, I will ask Shruti to take on the mic and summarize the whole session. Thank you, all of you. Shruti.
Your voice is like distorted. Hello. You change your voice now, please. Look the chats, bro.
Now, how is it?
Fine, bro. Finally.
Better.
Okay, I'll try sharing the screen. Is it visible?
Yes.
Yes.
Okay. These are the like the references that we went through, and you all would also be very interested to like go through all of it. We will send all of them in the either the channel, I mean either the Teams channel or the WhatsApp channel. So yes, that brings us to the end of A Story of a Star. So this is the end of the whole series. We have ventured from nebulae to stars to black holes. By the way, who wants to push their best friends into a black hole? Raise their hands. I mean, okay, I understand that people are not comfortable with telling this in the public forum. Mrudula, I'm not your best friend. But
I'm
anyways,
sorry, bro. I'm going to push you inside.
no, bro, thank you. But anyways, you should have some person in your mind who you want to push into a black hole. The best part is now you know that they'll be experiencing a space and time interchange. You'll exactly know their future, the singularity, which is actually an event in time rather than the widely perceived point in space. We can also predict their trajectory to some extent with the metrics that we learned today. And they can also serve humanity, involved in the Penrose process. Jokes aside, I hope you all learned something new from our session, guys. I know not everything would have been crystal clear to you all. We are also people just like you who are enthusiastic about unraveling the mystery of the universe. And we too are learners. And as we told earlier, we aren't here to teach astrophysics. We are here to lay the foundations for you to learn about it more easily, and our intentions were nothing more than making you all curious about black holes. And remember, learning is not a linear process, it's non-linear and it's a forever process. In my view, learning astronomy will make us realize how tiny we are and how much of a miracle life is. Astrophysics, on the other hand, will provide a proper scale for the vastness, and using math, we obtain a superior reasoning of the universe. Now you all know that math is the language of the universe. And at last, we presenters must bow in front of you all, audience, to have stayed till the end. You're crazy enthusiasts, come on. We would like to apologize for dragging our presentation by an extra of like half an hour or 20 minutes. But yeah, you all are the best audience we could ever ask for. Thank you so much, guys. And as I told in an earlier session, people who stayed till the end haven't lost their curiosity. Now I can tell it 100% and never lose it. It's the only thing that makes us alive. Thank you guys for joining. Please provide us your feedback. People can lower their hands down.
They still want to push someone in black hole.